So in today's video, we're going to be looking at the temperature profile of the bar that we introduced back in video 2. But instead of using explicit differencing, we're going to be using something called the Crank-Nicholson method, which is a method of implicit differencing where instead of just looking at the bar in a certain time, the same time step throughout, and using the temperatures at each point along the bar to approximate the next temperature, we're actually looking at both the temperatures at each point along the bar and the temperatures at the next time step at those same points. And I'm going to skip through some of the algebra, but the idea is essentially that we have the same bar, and instead of just looking at the positions along the bar, each delta x distance apart, we're also looking forward in time, and we're essentially taking the averages at each of these points and using that to approximate the temperature at the next step in time. So I skipped ahead and did the algebra for us. It looks really similar to, both sides of the equation look really similar to the equations we came up with in the explicit differencing video. The main difference is this u. U is just r over 2, just to keep it simple. And that just arises from, we're essentially taking the averages of the temperatures. But other than that, it's really similar. The left-hand side of the equation deals with the temperatures at the next time step, and the right-hand side deals with the temperatures at the current time step. And this allows us to set up this matrix multiplication. This is called a tridiagonal matrix, and that comes from, these three diagonals here. I'm not going to keep those circles there. Makes it hard to see. But essentially, we can multiply these two matrices. These are just the temperatures at each point. There is a T0 and a Tn that we've left out, which are just the endpoints, the constant temperatures at the end of the bar. And this is the resultant. This is the right-hand side. This is the right-hand side of the equation, and it's just set up in vector form. The one thing I want to note is that we have this u times t sub 0 and this u times t sub n. And we actually have that on both the right and the left side. We have the t sub 0 here, and we have the t sub n here. So since we're only looking up to the increment, it looks like I lost my n here. We're only going up to the increment of t times n, or t to the n minus 1. So when we add 1 with the position in the left-hand side of the equation, we get t sub n. So we can actually add that back over to the right-hand side of the equation, and we'll have 2u times t sub n. And then same thing with the t sub 0. We'll have 2u t sub 0. And with that, we can go ahead and make the Python program, which is the main part of this video. And we can show that our time step does not matter in this case. Any time step will give a accurate result. All right, so in this part of the video, we're going to go ahead and start the Python coding. I'm in the same notebook that we used before, so I'm just going to go ahead and copy and paste. The one change we do want to make is that instead of r, we're using u, which is just r divided by 2. And from there, we're ready to go. We already have our increments and our x-axis for the plot setup, so we don't need to worry about that. And instead of working with a matrix of the temperatures, we're going to be looking at, we actually have these set up above as well. Instead of looking at the matrix of temperatures, we're going to be creating a matrix or an array that has our three diagonals. We're going to be using a banded linear algebra solver to solve for those three diagonals. But those are the only diagonals we're interested in. We don't need to fill in this empty space on the top and the bottom of our matrix. So we're going to be making an array, and we want there to be 3 rows because we have 3 diagonals, and we want there to be n columns. Well, not n columns. We do know the left and the right boundaries, so we need n minus 2 columns. And then we're going to be setting up our 3 diagonals. We have a diagonal of negative u up on top. So that's going to be our first row. Our second row is going to be 1 plus 2u. and let me put that in parentheses actually. And then we're going to have a diagonal of negative u again. And from there we need to slice this so that we're excluding this empty space on the left and the right. Well, on the right for the or on the left for the top diagonal and on the right for the bottom diagonal. So let's actually start with the middle one because it's the simplest. It's going to be our second column here, or sorry, second row here, and we need to fill in all the columns with 1 plus 2u. And then on the bottom, we're going to put it in the third row. And we want to exclude the last column because we don't have a negative u in this column. So we're going to leave out the last column. And then on top, we're going to leave out the first column. All right, and then before we move on, it looks like I did the slicing wrong there. We're starting at the first column. The second column, and then excluding the first column, and then going all the way to the end. And then I was wrong. We do actually need to keep these here because if we run this block of code, then our temperature array is going to be all messed up when we try to run it again in here. But other than that, I think we're ready to start the coding for the for loop. So looking back at our matrix, looking at the right-hand side, there's pluses in between each of these, and it's the exact same equation as the explicit differencing that we did before, but with a matrix instead of our temperature array, and using u instead of r. So we're just going to copy and paste that, place this with b, and then replace these with u. And then the main thing that we have to worry about are these, oh, didn't mean to move that. We have this 2u t sub 0 and then this 2u t sub n. So instead of doing any fancy math with the matrices, we're just going to go ahead and append those. And then our last column is going to be 2u again. Oh, there we go. Nope. There we go. All right, and then I did have to fix this. I had brackets instead of parentheses, and then I had to add a multiplication sign in there. And so, oh, I also forgot these u's. All right, and then instead of updating our temperature matrix by doing the math inside the for loop, like manually per se, we're going to use solve bandit instead, which will solve our matrix system for us. And the first thing we have to provide is our, it has it right here. The number of non-zero lower and upper diagonals, which is one of each. Then we just have to provide our matrices. And from there, we should be good to go. So the main thing we were trying to prove here is that we can change the time step to pretty much anything, and it won't affect the stability of it. So I'll just bump, oh, we still have it at 0.51. Let's bump it up to 0.7. We'll run that and run this again. And as you can see, our graph stays stable, whereas if we were to run the explicit differencing graph, it looks like I got rid of my R. I'll put it back in just so we can show you. So when we run the explicit differencing graph, we start getting unstable solutions. So in the next video, we're going to be talking about why the Crank-Nicholson method provides that stable solution using the von Neumann stability analysis.